So in Chapter 9, we'll be looking at trying to determine a reasonable range for a population parameter that's not known. And in 9.1, we'll start with looking at the population proportion. So the idea is if you don't know the population value, whether it be mean, standard deviation, proportion, then the first thing you would do would be to conduct some form of survey or poll to determine what's called a point estimate. So that's just a fancy name for these things that we've kind of been talking about here and there. Things like X-bar, especially, the one we've been working with lately. The idea of you can find a sample mean if you are trying to estimate or approximate what the population mean would be. Same with a sample standard deviation or a sample proportion, right? P hat, as we saw it, to estimate the various population parameters. If we just look at this first example, we're looking at a situation where a poll was taken and 1,783 voters were asked if they favored or opposed the death penalty for a person convicted of murder, and 1,123 were in favor. Right, so that's the information taken from a nationwide sample, right, nationwide survey. So it says obtain a point estimate for the proportion. Okay, so simple enough. If you're looking for the proportion, right, P hat is what we're trying to calculate here. Well, then that would be the 1,123 that were in favor out of the 1,783 that were surveyed. And we just throw that into a calculator. And if we round that to 4 places, 6298, right? So 0.6298, or roughly 63%, right? Now, that 63% came from this sample, and the sample involved almost 1,800 people, but that's out of the entire nation. So to look at this number, we wouldn't say that we feel like the proportion of Americans that were in favor of the death penalty for someone convicted of murder is exactly 0.6298, right? This is a sample value. Now, the question of whether or not the population proportion is somewhere near this, that depends on a couple different variables. One of which being, how many people did we sample? 1,783 isn't a huge number when you compare it to the millions, 300 plus million people that live in America. But it's a good number of people. It's way better than if we'd sampled, 17, right? So that basic idea that the more people that are sampled or the more individual pieces of data that are in your survey or sample, the more accurate we expect this to be, right? But again, we don't expect it to be exact. We don't expect that to be the value of P, right, of the population proportion. But it could be close. So when we talk about being close to that value, close to a point estimate, that's when we end up, one way of discussing that is with something called a confidence interval, okay? And the word confidence is really the key word, the idea of how confident are we that we're close to that population value. Now, the understanding here is we don't know, right? We will not know the population parameter value. This particular image I've got here is involving mu, so I'm back to talking about the average. But the idea is that we want to create an interval. So an interval is this idea of being on either side of your point estimate. Your point estimate's a number, and you want to look around it, right? The idea would be if this was the P hat we just found, it's a number. We're going to allow ourselves, if this is like a number line, to look a certain distance left and right of that one number. Because again, we don't expect that to be the number. But what about the possibility that the population proportion is near it, around it, right? That's the idea of a confidence interval. Now, a confidence interval can be affected by a couple things, one of which is what level of confidence do you want? How confident do you want to say you are that the population proportion would be inside of a certain interval? So for these levels, generally you'll see them represented as percentages, normally upper 90s, 90, 95, 99, generally speaking, in this class especially. So that's the level of confidence we're going to see. This notation that we use here, don't let that really throw you off. We'll talk a little about alpha here as we get into the computational side of things. Imagine it as, notice if the alpha wasn't there, it'd be 100%, 1 times 100%. So alpha is just a decimal being taken off of 1 to give us some number close to 100%, right? For example, if we looked at 94% for the level of confidence, well then that means alpha is 0.06. because you would subtract 0.06 off of 1, and you'd be left with 0.94, and 0.94 times 100 is the 94%, right? So that's all alpha is as a decimal, how far below 100% are you in terms of how confident you want to be, okay? Now, the idea of what this confidence really represents, it's kind of tricky. We were kind of specific about how we word it. So notice, and then I didn't create 100 confidence intervals here in this image, but the idea of if you were looking at a confidence interval of 94%, that's going to be a certain width, a certain interval length from left to right to each side of your population proportion. So a 94% level of confidence implies that if we took 100 different intervals based on 100 different samples, we would expect 94 of the intervals to contain the parameter, but 6 wouldn't, okay? Now, boil this down to this set here, right? And so of the ones you see, what we're saying is, here is the actual parameter. And again, normally you do not know this. But if you look, these are vertical number lines essentially. Think of each of these as if it was an interval. Like this interval was created with finding whatever that is as the actual point estimate, and then allowing yourself to look above and below it to create that interval. This interval was found with this point estimate, looking above and below the same distance. Notice these are all the same length. So we're saying we created an interval that came from how confident we wanted to be, but then we found all these different point estimates, the centers of each of these lines. And notice how the vast majority of them have the population parameter in them, right? It intersects all these, but notice it's just outside of this interval here. It's inside of all these intervals here, but it's just below this interval here. So it's not in every one of them. That's the idea. That's the idea of this level of confidence. And we can't really go for 100% level of confidence, because to do that, theoretically, we would have to include almost all the numbers, and then your interval is kind of pointless. So you want to balance what's a good level of confidence with not an interval so big that the interpreting it is kind of meaningless. But that's where each of these intervals comes from, is whatever the point estimate was. So we took a sample and got that as a point estimate. And then this thing called the margin of error is what's being added and subtracted from that number to say how high up and how far down are we looking when we make this interval and say, we think the parameter would be in here, right? And again, that comes with the level of confidence. So we would say we are 94% confident that the parameter is from here to here, if we took that sample. But later on, we took this sample, we'd say we're 94% confident the parameter, mu, is between here and here. So each one of these is its own interval, right? So this margin of error, the distance, the length of this interval that you're making, how far above and below the point estimate you're allowed to look, is based on 3 things. And let's talk about these really quick. So level of confidence. Again, like I mentioned, if you want to be more confident in your interval, well, then you're going to have to increase your margin of error, right? To be more confident means you want to include more numbers. So there's your point estimate, that number, that dot, right? That single number. And so you start allowing yourself to look at more and more and more values. Well, you can be more and more and more confident, but the population proportion's somewhere in there. So raising the level of confidence raises or increases the margin of error. Now, back to the idea of sample size. The more, I'll say, people you sample, or the more data values in your sample, so the more your sample size increases, your margin of error actually decreases, because, like we said earlier, with the poll of 1,700 people versus 17 people, the more information you take in, the more accurate you expect that one number that you got from that, whether it's sample proportion or sample mean, whatever the sample value is. So the bigger your sample, the more accurate representation you think that sample statistic is of the unknown parameter. So bigger samples means you don't need as big of an interval left to right to be confident. So that can affect the size of the margin of error, the size of the interval. And lastly, this should be hopefully obvious, the standard deviation of the population. If you've got a data set that's really spread out, well then no matter what you're dealing with, you're gonna have to have a confidence interval that allows you to look further left and right to see more of your data. If you've got a data set that's very compact, a very small standard deviation, and all your data is very close together, well then you don't need a big confidence interval to include a lot of data. So that's kind of the idea of how these different aspects will affect the actual interval we're going to create. Okay, so now for the formulas and the, we'll call the check again here. So these two things just define the mean of the proportion and the standard deviation of the sample proportions. These are going to be worked into the main formula that you need to make sure you can use. But we've got this guy right here, the check. This is the same check as we saw in the previous chapter, where we're going to have to work with the assumption that we can work with a normal curve here. And the only way that we know that these proportions or the distribution of the sample proportions follow a normal curve was if it passed this check. So we will want to make sure we're checking this bit of information here. And then, actually, I just realized there's a typo. That should be p hat. And so then as long as that's the case, we can move forward. Moving forward, you've got what we'll call the upper and lower bound of your confidence interval. And I represent them this way, but I'll talk about a shorthand way to kind of think of them as well. So the upper and lower bound, I know they look like a lot's going on here, but really, truly what it is, I'll kind of push this page down a bit, is we're talking about an interval for the population proportion. So notice both of these have p hat. You had to take a sample, you needed a sample proportion. But then you're going to either add or subtract this expression, right? Now, the z alpha over 2 we'll talk about here in a moment, but then this is just the value, the formula for standard deviation. So this expression right here, notice this is the margin of error. That whole bit right there is telling you how much you want to add and subtract from that center point, that center sample proportion, to say I can look this far up and this far down in my interval, my confidence interval of values. Okay? So, with that, again, this is one way to think of it. You're going to see me when I do it in calculation, more so just kind of calculate this thing, calculate the margin of error, and then add and subtract it from p hat. So feel free to go about your calculations that way. Oh yeah, here's the check with the p hats written. This I think we talked about back last chapter, and again, it's not something we need to check. It's something we're going to basically be given or told or just assume that our sample size is not too big. It's going to be less than or equal to 5% of the population. We've seen that in the past as well. So let's take a look at the idea of this z alpha over 2 real quickly. Okay, if you remember before, z alpha, we learned this in the last chapter chapters when working with the normal curve. Whenever we saw z alpha, that was the idea, or z sub alpha, that was the idea, if I just kind of do a quick review here, that was the idea of having a normal curve, knowing that there was some, think of it as a tail, some shaded region that had an area of alpha, and the z-score of that boundary is what we called z sub alpha. In other words, the z-score with alpha to its right? The z-score with an area of alpha to its right. So this alpha, again, being this distance, the difference between 100% and whatever your confidence level is, right? So again, if it's 90%, then alpha is a 0.1, like 10%, right? That's what alpha represents. But we want z of alpha over 2. So we're going to take alpha and divide it by 2 in order to determine this kind of shaded area. And we'll talk about that and why that is here. Because with a confidence interval, we need both a low and a high, right? We need a low upper bound and a lower bound. But those need to be symmetric. They need to be the same distance from our center, from our point estimate. And so what z alpha over 2 is really having us do, it's having us imagine the normal curve, but take that alpha that we want kind of outside of our confidence level, right? If we're 90% confident, 90% inside, 10% outside, but break it up so that there's alpha over 2 on this tail and an alpha over 2 area on that tail. And so this is what we're really finding. That's z sub alpha over 2, and technically what this is, it's the negative of z sub alpha over 2, because these are symmetric. These are the same distance from the center, same amount of area, right or left. So this z sub alpha over 2 z-score is positive, and this one is just the negative. But again, you don't even need to worry about that because that's just built into our formula where we're adding it here and subtracting it here. This is really taking care of what this does for us. It gets us these two important values that are the endpoints of our interval.